Hello. Okay, I should have 3 handouts. The first is the team signature sheet. So, and I have also section 1 and section 53C.
Section 53C up yet?
53C, 53.
Yeah, is it up yet? I just looked at the website a minute ago.
Yeah, I know. You have the hard copy. I haven't put it on yet. Okay, so can you perhaps let me put over here?
It's on the.
Right, so the team signature sheet with all of your names on now. So you can just send one team representative. Section 1 here.
Oh yeah, okay.
And keep a copy for those
So it's
teammates
not
who
up
are
on
not here, and also
the
section 53C.
synopsis there.
Okay, so I print now 4 pages on one.
He's giving us
So
one of them.
that would also save weight and paper. Zoom in here.
Yeah, I printed this out already.
Maybe don't pick up the loose leaf.
I'm never doing that, dude. I'll pay for it. I like being.
For myself.
It's not like he pays for it.
Yeah. I'm just curious how long we're going to do it
Yeah. It's usually a week, 2 weeks.
Nothing left for me. Maybe I still have it for me. Yeah, I have the loose leaf here, I think. Oh, okay, yeah. Be sure to keep for your missing teammates.
They're not here.
They're not here. Yeah, if you need to keep for that, yeah. Because I'd like to not having to carry back and forth. Oh, anyone having extra copies?
Yeah, I got section 1 extra copy.
Yeah, if you have any extra copies, please. Because this is for me. Okay, so let me bring up the mask. All right. This is the extra meeting for yesterday. What I call meeting 5 with an X for extra meeting. That's essentially a review of scalar differential equation that you have seen in the differential equations course. Okay. So and I have the lecture notes, my lecture notes, as well as the videos that I created, lecture videos. Let me see. Yeah. So lecture notes, for example, section 1. Then you have the videos in 2 parts. And then section 2, you also have the videos in 2 parts, right? So for those of you who need to review, you can make use of these resources. And I gave you the hard copy of section 1. So for those of you who came late, check with your teammates, because your teammates probably kept a copy for you. And also section 1 on 4 pages on 1 sheet. Okay. And same thing for section 53C, which we will do after we finish section 53B. So I hope that, I would encourage you to print out a hard copy. Even printing 4 pages on 1 sheet, it's very, very readable, very, very legible, because the font size was large. And in the back, you can write notes either on the lecture notes or on the back of the sheet. Okay, so that's about the section 1, and that's also related to report R1, the problems in report R1. So I'll talk about that. Let's see, what is this? Okay. Let's bring up, the R1 problem can be also accessed through the portal. Okay, so if you go through the portal, I have a link. Let me zoom quick, so that's easier to see. So here is the link for the report problems for report 1. Okay, so you can access through various means. So the portal is very compact, so it's load up very fast, or you can also access it here, because whenever I do something, I always have a few points as a reminder for me in the daily summary. Okay, so this is the the statement, due date, and so please look at that. Show details of your work from scratch. Is there anyone who, sorry?
I'm just trying to figure, the due date is the 21st, right?
January the 21st.
Okay, so that's the due date.
01.2, January the 21st. From scratch. Yes, direct.
You said that there was a free textbook you were going to give us.
Yeah, let's. Yeah, we don't need that yet.
So we can use like textbook for some of this stuff. Or
Sorry.
the textbooks, like you can't use the textbook for any of this.
Say that again.
We can't use the textbook for any of the problems.
You don't need. You have my notes here, link here. Okay, we'll talk about that. But let's. From scratch, is there anyone who knows the origin of this English idiom? From scratch. This is English language, right? What does it mean from scratch? How do you understand from scratch?
It's like when you make something, like when you are cooking, you make something completely with fresh ingredients.
Cooking?
Yeah, when you make something with completely new ingredients.
Making completely new dish? Okay.
Wouldn't
Or
it like
cooking.
when you had a tablet, like you used to like carve into it, you scratch into it?
Okay. The usual meaning would be from the beginning, right? I guess everyone would understand that. But why how do you connect from the beginning to from scratch? Actually, if you check out, some people say that it's coming from farming, chicken scratching the dirt and getting the dirt into their gullet in order to grind the food. But also there's another origin is from cricket. The scratch, you draw a line on the ground, scratch the line on the ground. That's where the batman would stand. And also later on it's used in foot races, where the scratch line is a line that you draw on the ground. That's a stopping line. Okay, and so without advantages, so those who need some advantages can start ahead. So from scratch means starting from the beginning without any advantages. Okay, so show your detail from the beginning, completeness, that's what it means. And to each problem I have a link. So for example here you see section 1, problem 1.1. So you can click at section 1, you see my lecture notes, and you look at problem 1.1, that's where the statement is. Okay, there's no need for any text here. If you would like to read something to complement, that's fine. But this is where the lecture notes and the lecture videos, are on this topic, and the problem number is also listed in my lecture notes here. So I have lecture notes, lecture videos, and we'll come back to this problem soon. Okay, so the problem numbers are listed here. Okay. So everything is very convenient. There's a link, just click at the link, brings up the lecture note, and I printed out my lecture notes section 1 to give you as a hard copy too. So you have a soft copy, hard copy. It's very easy to find. If you are still confused, please feel free to ask. And you have a team, so your teammates can also help out as well. And I have provided the self-help solutions, which were the best solutions and best reports from last semester. I really suggest that you try not to look at the best solution, do on your own, and just if you get stuck, then look at that. But I'm here, Michael, your teammates. There's a lot of resources. Okay, so and I have also reduced the number of problems that you need to report in your report. So there's a lot of things that have been, a lot of steps that have been taken to really make your experience smooth. Okay, so and by the way, if you have problem with understanding the problem statement, the resources that were provided, the best solutions, the best reports were there also. Okay, because students are expected to rewrite the problem statement from scratch, meaning not copying from my lecture notes, because for example, if you look at my lecture notes, the statement is really depending on, for example, this statement here, it's very short, very concise. Don't just copy it and paste into your report, because that, for example, the goal of the report is that it would be something that would be helpful to you 1, 2 years, 3 years down the line, when you need to go back and review, right? So if it's something like this, it's not sufficient, it's not self-contained, then you have to go and look somewhere else. Okay, so you want to rewrite the problem statements as self-contained as possible. And you see, the reason that I write as compact like this is because I have already written, in a way, if you think whatever I have written in my notes, upstream, that's part of the problem statement. Okay, is it clear to everyone? All right. And you have the model reports. Talking about the model reports, so if you bring up the portal and you go to reports, And here I provided some really beautiful work. This is graduate level, but you know, I have also provided reports at the undergraduate level as model report, in addition to the best solution and best reports that are in the resources. Table of contents, you see, when you read the title, it's really give you an idea of the content of the problem without having to look at the problem. That's what you want, right? You don't want to have just the numbers, but have descriptive title in the table of contents. And there are more that you can go through and see what would be desirable. Okay, yeah, here I mentioned best report to emulate. Oh, I just moved my, best report to emulate at the top. Yeah. Okay. All right, so that's the model report there. This is the portal. And so you have lots of resources and where to look at to emulate. Excellent. Okay, so now last time, so I had mentioned. I remember, this is just after I came back. I remember. So Kevin, right, team 6, and Brennan. What team number, Brennan? Is it team 3? Yeah. So doing, as I advise you to really look at this document every day, and if you see that your name is missing, send me an email. Okay. Yes, you have a question.
How would you like us to submit the reports?
Through Sakai. Yeah.
Okay.
There's a requirement of how to submit. Yeah, PDF, all PDF. Yes, please. No hard copies. So let's answer. I'm sorry. I know your name. I need to learn your name. I know I have written it up here. Morea. Okay. Yeah. Yes. Okay. If you go to report 1, statement you see here, course report submission to Sakai requirement. Yeah, so please look at this. Okay. Yeah, so everything is really make it in such a way that it's convenient. Just one click away from what you need, the information that you need. Yes.
For the lecture videos you put up on Thursday, for the lecture videos you put up on Thursday,
Yes.
can we come and see that in person? Like when you do them, when you film them?
Oh, this is what I did, and so all you need is just to click at the video, and you should be able to see it on your own at your own time, anywhere. It's already, for example, here, if you click on this, you have the video played for you.
Okay.
So it's
This is
talking about video and the audio. For example, if you want to listen to the audio, or you want to synchronize the audio with the video, the sound of the video is pretty good because it's pretty close to me. But if you need to really synchronize the audio that I recorded through Audacity and the video from the camera, if you use Google Chrome, you can just click and play. You don't need to install the codec, audio codec. But if you want to download and play on Windows Media Player, then I gave the instructions at the top of the document of how to do that. Okay. All right. So yes. So indeed, we have confirmed that it was Kevin and Brandon in 3. And if there's anyone else, please let me know. Yes, I have gone through all of these points. Now let's meeting 4. I think. Is there any further question? I think it's very convenient, like I said. I mean, just at the click of And yeah, so Kevin was asking about 53C, seeing as a lead. Okay, I just didn't transfer it to my daily lecture summary. Okay, so if you have further questions, I can entertain any questions. If not, then let's.
You got one right here.
Yes. Yeah, I need to learn your name. Yeah, so we'll come to your questions and Kyle's questions too. I have it written here. Question that you asked me at the end of last class.
Well, one more question for the report.
Yes.
Is it just one report that we submit for the whole team?
One report per team, yes.
And
unless if you do individually, then yes.
and one person will submit it for the team?
Yeah, one representative of the team submit for the team on behalf of the team, yes. Suppose that you have a team of 6 or 7, and if 1 or 2 wants to do individually, and then the rest do together, yeah, but you know, then there would be 3 reports, right? You mean one. If anyone who wants to do individually, then submit on their own, and the rest would submit as a team. Okay, is it clear? Maria, yeah, question.
Nice Google Doc.
Okay, right. So let's meeting 4. You know, this is as a way to have a continuity between what we did last time, and this is the note that I have annotated, my handwritten note from last time. And so this is the D'Alembert force. I think Kyle at the end of the class asked about the meaning of the minus sign, and I gave 2 times in the last lecture the physical meaning, you know, of the an accelerating car, and your body is pushed back against the seat. And what's your name again? What's your name?
Matthew.
Matthew, what team number?
Team 8.
Team 8, okay. Matt also asked me a similar question, and so I thought of a different way to explain this. And so let me bring up my journal tool. Okay. And I need to turn off this one here. Okay. Right, everyone heard of the famous expression F equal to ma a long time ago. So let's say if you work only in one-dimensional, right, just one-dimensional case, and let's say if you have a particle moving on a straight line, and let's say if this is the particle, you can have several forces. Okay, that is applied. You know, I mean, even though it's in one direction, you can enumerate it. Okay, and so let's say this would be the direction of motion, right? Let's say the displacement, which is time dependent, and let's say you can think of this as a force F1, also a function of time, force F2, function of time. So this force F here is really the sum. You can think of this as the sum of all the forces acting on the particle or the body. You can write F as the sum of all the forces Fi, and that's time dependent, right? I going from 1 to whatever. Okay, so in this example, 1 to 2, if you like, to be all right, and of course, clearly, F is also time dependent, right? Because of the all the individual forces are time dependent. Okay, so this is one way to see. Okay, you can see Newton's law as F equal to ma here. But you can also rewrite this easily so that you can see as a sum of forces equal to 0. Okay, just by moving the inertial force to the left, and therefore, right, you have sum of forces. And now when we talk about sum of forces, not just the applied forces, but also the D'Alembert force, right? D'Alembert force is minus the inertial force. Okay. Yes, no, Anderson.
So could you say that the D'Alembert force is a restraining force causing the mass to move with the system?
You know, inertial force, essentially, it's just a representation of the inertial force. You know, as think about the car accelerating, right? When you accelerate your car, your body is pushed back against the seat. So that's the physical explanation, and this is the mathematical explanation of why the minus sign and why you sum the forces. Okay. So that's that's, I think, I hope it's clear to everyone. And you can also, as I mentioned, look ahead. You know, this is the fall 2014 portal, and if you go to part A of my daily lecture summary, and you look up, you know, do a find, right, a search for D'Alembert force, you see that I have a critical thinking question by a student in the class. Yeah, let me zoom in to fit. Okay, and I have written also something down here, my handwritten notes in class, meeting 26. And if you bring up meeting 26, and you see that indeed I also explained something very similar to what I just explained to you. But this class is more advanced than last class because you asked this question much earlier. Okay, so so this is another resource that you can use, and I will link into yeah, I can do that right now. I just need to copy and put over here. Okay, and I need to mark down that this is fall 14. Okay, so that you see that this is from fall 2014 edition or version of the course. Okay, so let me just I'll reorganize later. Okay, I just need to remove all the links here, and this is meeting 6. So meeting 6, when it's not preceded by a semester, then that means it's the current semester. And for this, from fall 2014 semester, I would put here. Okay, see also. Okay. Is it clear to everyone? Okay. Please feel free to ask if you have further questions. This part I should have put in magenta because that's what we did in the last lecture, in the previous lecture. Okay, so I'd like to move forward. So let me close this. I think I can close this now. And I'd like to continue with the discussion and finish section 53B, hopefully. Okay. So probably very familiar with this now. You have the hard copy, so let me just use one window. We have gone through this. This is element 2 and element 3. We have gone through this, and we started with the equilibrium of the mass, and there was the issue of the dollar bear force, right? So now everyone sees that the dollar bear force is pointing in the negative direction, meaning opposite direction to the assumed positive direction of motion, right? This is the direction of motion. Okay, it's an algebraic quantities. Okay, meaning that it can be plus or minus. All right, so I just explained why you sum forces equal to 0, even though this is dynamic, but it looks like static, right? Because the dollar bear force essentially with the minus sign allows you to think like statics. You know, sum of forces equal to 0, but really you do dynamic formulation. All right, and so now we have, you see the internal force at B due to element 1, because we are looking at, let me zoom out so that you have the picture in mind. Right, we have two internal forces at B, but one due to element 1 and the other is due to element 2. And we have obtained the force displacement relation for the internal force at B due to element 1, and that is given in this expression, where K1, recall, is the spring constant of element 1, C1 is the damping coefficient in element 1, and dA is the displacement at node A of element 1, and dB is the displacement of node B. Okay. Here we have not included the boundary conditions yet. You know, we'll do that later. And D prime, dA prime, and dB prime are the velocities of node A and node B. And likewise for the force at B belonging to element 2. The only difference between this expression and this expression is that you have the, you know, be careful. This forces is on the left of element 2, okay? Whereas this forces is on the right of element 1. So therefore the sign, you need to be careful with the sign. But from the matrix expression that we obtained earlier, this is the expression for the force at B due to element 2. And so you see the spring constants K2, the displacement at B and at C. Remember, B now is on the left of element 2, and C is on the right of element 2. Okay. And here is the damping force in element 2. You have the damping coefficient C2 and the velocity at B and velocity at C. All right. So summing, you know, replacing these two expressions in this sum of forces equal to 0, remembering the D'Alembert force minus the inertial force, and not forgetting the applied force, you know, gap FB as represented up there. That's it. Then you have the equation of motion for the mass MB as shown here. Okay, zoom in. It's just a direct substitution of these two expressions, right, in the sum of force equal to 0. And Jackie, you asked a question that
I figured it out.
Sorry?
I figured it out.
You figured, okay. All right. So if you have any questions, please feel free to ask. Otherwise, you see, we proceed exactly in the same manner. We look at the mass B. Now we look at the mass at C, right? Also known as M2. That's the fifth free body diagram. Same story. Let's zoom in. Right? Let's recognize the forces now. You know, everything is the same except the names. Okay. Point C. Mass MC, also denoted as M2 because this is the second displacement of degrees of freedom. Okay, D sub C is the same as D2. You cut to the left and to the right of this point, you have the force at C due to element 2 because element 2 is now sitting to the left of point C, and to the right of point C you have element 3. So the internal force due to element 3 is the force F at C due to element 3. Okay? The inertial force, because the assumed motion is always positive, so this is the displacement of this mass. Again, algebraic quantities. If you do the computation, and if the sign is negative, it just means that the mass goes in the negative x direction. Okay? But algebraically, you always assume positive. Then the D'Alembert force is minus the inertial force, right? And the minus sign is included in this arrow pointing in the negative x direction. Okay. So, and you do exactly the same, and so please do this problem as a self-study problem. It's identical to what I did above for the mass at B, right? Sum of forces equal to 0. And then you find the expression for the force Fc due to element 2 in terms of the displacement in element 2, and the force Xc due to element 3 in terms of the displacement in element 3, and you substitute into that dynamic equilibrium equation, right? Then you obtain this expression. Okay, let's recognize a few things, okay, before we move on. So you see mass at C, yeah, let's zoom out a little. Inertial force plus damping force plus spring force equal to applied force. Remember that structure. Inertial force plus damping force plus spring force equal to applied force. Inertial force, mass times acceleration. Mass at C times acceleration at C, right? dc double prime. This damping force looks a little more complex. Okay, you have minus C2 and then plus C2 plus C3 and then minus C3. So what you want to remember is the following. You know, we are like an observer sitting on point C. Okay, on the left of point C is point B, and on the right of point C is point D. When you sit on point C, you add the two contributions from C2 and C3. Okay, that's the damping coefficients associated with the displacement or the velocity at C. But you know, you have also a contribution due to the velocity at B because point B is also moving, right? But with a minus sign, okay? Minus C2 dB prime, velocity at B. Likewise, point D, in general, you know, without applying any boundary conditions yet, you also, the point D would move as well, and the contribution to the dynamic or the equation of motion of point C is this term, and that has a minus sign, minus C3 D prime, D prime, right? Velocity at point D. Now, observe that the mathematical structure of this term is exactly the same as this term. Okay? The only difference is just the symbol. Minus C2 dB prime, minus K2 dB. Right? C2 plus C3 dC prime, K2 plus K3 dC. Right? Here you have displacement, here you have velocity. Okay?
I understand why the C2 dB prime and C3 and DD prime are negative, and then those middle terms for both lines, what makes them positive again? Why are they positive rather than negative?
Well, you know, this is first observe this, and I'll come back to the matrix. Okay, you remember that the stiffness matrix is not all positive. We have minus k, and then sorry, k minus k, and then minus k, right? So you know the negative sign essentially comes from the assumed positive direction of the internal forces. But let's observe this. You know, this is the observation that the structure, the mathematical structure of the damping term is the same as the mathematical structure of the spring force. The difference is the coefficient, right? The name of the coefficients: damping coefficient, spring coefficient, or spring constant. Here you have velocity, and here you have displacement. Otherwise, the sign is exactly also identical: minus, plus, and then minus. Okay, the plus sign is corresponding to the displacement on the point that you are looking at, whereas the minus sign is associated with the nodes to the left and the nodes to the right. And let me bring up the same lecture notes, but on a different window. So to review for you, yeah, what I just mentioned to Kyle. You know, you could have also asked the question, the same question that Kyle asked. Why there's a minus sign? You know, why not everything is positive from here, right? Because even if you look at the force FB up there, maybe let me open up the mask, because you may right. If you look at this equation by itself, you see that it's not all plus, it's minus. And the reason that there's minus is because you are looking at the stretch. Okay, dB minus dA. You know, think of 2 points are moving, right? So this point may move with a larger displacement than this one. But if you are an observer sitting on this point here, and if you want to look at how much the spring is stretched, you have to take the displacement at this end minus the displacement at this end, because this end is also moving, and you want to sit on this one, you know, to see the difference. Okay, so the minus sign already started from here. Okay, so be careful; it's not all plus sign here. All right, so. Let's see how much time. I should not, give you some time to think while I do this. Use the opportunity to think. What team number?
6.
Team 6. And Mark is team 8. Anyone? Anderson? Team
7.
Team 7. Okay. If anyone else that I forgot contribute to the understanding of the class, please.
Ask a question about the book.
Yeah, ask a question
About the book before.
Okay. Okay. Yeah. What I meant is understanding of the content of the lecture. Okay. So for administrative, so in the future administrative questions, that's extra. That's separate. Okay. All right. So let me wrap up here. We have 5 minutes. So now you apply the boundary conditions. Point A is fixed. Point B is fixed. So displacement at A is 0, and therefore velocity at A is also 0. Displacement at B is 0, so that equal to 0 at any time. Okay, and therefore velocity at D also equal to 0. And and here the next equation is simply just to instead of writing with the letters B's, you know, change it to 1, right? Because mass B has displacement dB or D1, the first degree of freedom. And likewise, instead of writing F sub C, you write F sub 2. So we change all the indices into the numerical representation, right? So D sub C is D2, the second displacement degrees of freedom. Then you see this is the structure, and this is what you want to remember. Again, right? This is the equation of motion. It's a two coupled second order ODEs written as you have the inertial force, that's the mass matrix, times the matrix of the acceleration. This is the mass matrix here. You know, M1 and M2 are the masses of at B and at C. The off-diagonal coefficients are 0. The second term is the representing the damping forces. This is the damping matrix. Note on the diagonal you have C1 plus C2, C2 plus C3, but minus C2 minus C2. And likewise, the stiffness matrix is very similar to the damping matrix. From the point of view of mathematics, the difference is just the symbol, right? On the diagonal, you have the sum of the two stiffness spring constants, K1 plus K2, K2 plus K3, and then minus K2. All right? So this is the system of two equations that we want to solve. Okay? And that's what you learn. That's what new in this course. Last question before you write the summary. Why do I say that this is two coupled equations? Why are they coupled? In other words, why are they not independent? Let's say, Kevin.
Well, they both depend on some of the same stuff. Like they both depend on the same damper and the same spring constants, right? Close, no cigar. All right.
Anderson, let's say Mark Anderson, you contributed a lot.
They both.
Somebody new.
They both depend on the displacement of the mass.
Okay, boss. Let me bring in someone new. Yes. Let me give you a hint. This is a hint.
So left side has 1 and 2, and right side has 2 and 3.
Left side has 1 and 2. The right side has 2 and 3. Okay, so let me give the answer. Look at this equation. You know, you have the displacement at B as well as the displacement at D. It's like two unknowns within the same equation. Okay. So if this equation depends only on one unknown, then it's independent from the other equation. Here you have two equations, and in each equation you have the presence of two unknowns. So please write the lecture summary, and we'll continue next time. If you have any questions, you can write in the lecture summaries as well. I know it takes some time to think about this, okay? So if it's not obvious now, you need to think about it.